Previously made a video where I tried to show how you can take a more complicated circuit and simplify it by looking at resistors in series and how two resistors in series can actually be thought of as a single resistor with an equivalent resistance. And so in that video, what I said was the 9-volt battery was going to create a 9-volt potential difference between the positive and negative terminal, which is to say that on the negative terminal, the voltage would be 0, and on the positive terminal, the voltage would be 9. And so if we assume that the wire does not offer resistance, then at all places that are just wire, the voltage does not change. And so it would be 9 volts at the terminal, it would be 9 volts here, it would be 9 volts here. And then when it encounters the first resistor, it's going to go through a voltage drop. And so remember by Ohm's law, V is equal to I multiplied by R. And so if we have, say, a resistance of R1 and resistance is in units of ohms, and then let's say we have another resistor R2. So at the positive terminal, it's 9 volts, and then as you go on the wire, it's 9 volts, 9 volts, and then there's going to be our first voltage drop. And so our first voltage drop is going to be V1 equals IR1. The current is the flow of charge through the circuit, and it's going in the direction you see with the arrow because it's going from the positive terminal, which is of higher potential, to the lower terminal, which is of lower potential. So positive terminal to the negative terminal, which is of lower potential. And so you now have, so like if I was to like put like an X right here, that potential would no longer be 9. Rather, that potential would be something along the lines of 9 minus IR1 because that is the voltage drop across the first resistor. Now, everywhere you see an X here, it's going to be the same until we get to the second resistor. And then there's going to be another voltage drop, and that voltage drop we'll call V2. And you have the same current going through the circuit, but you have a different resistance R2 now. And so then look at how, if you go to the other side of the resistor, there's nothing but wire until you get to the negative terminal of the battery. And so we can go backwards here. We can say 0 here, 0 here, 0 here, and 0 on the other side of the resistor. So that means that our total resistance goes through two voltage drops. It equals the first voltage drop plus the second voltage drop, which is equal to I R1 plus I R2, and that is equal to I times the quantity R1 plus R2. And so this term right here is what I called the equivalent resistance for two resistors in series. And the key here is that you recognize that when you go through the first drop across the first resistor, the voltage before you go to that first drop is not the same as what the voltage is when you begin the second drop across the second resistor. So if you have a series of resistors, it turns out that the equivalent resistance, I'll put a little S here for series, is just simply equal to R1 plus R2. Now, if you had a third resistor in series, it would be R3, and it actually goes out to R infinity. So you have an infinite number of resistors in series. The equivalent resistance is just simply adding them together. And so then you could take what looks like a more complicated circuit with a bunch of resistors and think of it as just a circuit with a single resistor where that single resistance is equivalent resistance. So now what I want to do is I want to explain how you would do this if you have instead resistors in parallel. And so again, I'm going to say we have like a 9-volt battery, and so that creates a voltage of 9 volts at the positive terminal and 0 volts at the negative terminal. And so again, your charge is going to flow from the higher potential at the positive terminal to the lower potential at the negative terminal. So once again, when it's just wire, it would be 9 volts here, 9 volts here, 9 volts here, 9 volts here. Now here's the difference between when things are in series. At this point, you can have charge either go up and through R1, or you can have it go down through R2. But look at both R1 and R2. It's still just wire until you get to them. So it's still 9 volts here, 9 volts here. It's still 9 volts here. It's still 9 volts here. So the difference between when things were in series is that when resistors are in parallel, it means that the voltage drop across them is the same. And that's not the case in series. And so that's what makes parallel resistors parallel, is that they both have the same voltage when the charge begins to go across them. And so what we can think of now is we've got on the negative terminal, we have 0 because there's a 9-volt difference. So if I work backwards, it'd be 0 and 0 and 0 and 0. Because remember, if the wire doesn't have resistance, then we're just going to say that the voltage remains the same. So look at this. On the other side of both resistors, the voltage is 0. So on one side of each resistor, the voltage was 9, and on the other side of each resistor, the voltage was 0. So the voltage drop across each of these resistors is exactly the same. That's what it means for two resistors to be in parallel. And if I had, say, a third resistor where the voltage drop is across the same, you would say all three of those resistors are in parallel. And so I want to show you how you can calculate the equivalent resistance for resistors in parallel. Unfortunately, it's not as simple as in series where you just add them together. So that being said, Ohm's law still very much applies. And so it turns out that if you can imagine you have a current that begins at the positive terminal, it's going in this direction, it's going to actually hit a point where it's going to branch. It can either go this way or it can go that way. That is, the charge can flow across the resistor 1 or it can flow across resistor 2. And eventually the charge links back up and then it flows in the direction you see here until you get to the negative terminal. Because again, positive terminal, higher potential, negative terminal, lower potential. And you're going to have charge, if provided a path, moving from the higher potential to lower potential. Just like if you had some water at higher ground and you had a path for the water to flow, that water is going to flow from higher ground to lower ground. So when we have some total current, when we think about when it goes into the junction, whether it goes across R1 or it goes across R2, we can call when it goes across R1, we can call that I1, and we can call I2 when it goes across R2. So I hope you can see, I'm going to put like a big blue here. That's the junction. And it's in the current, which is this all the current at that point, I total, it's going to split and either go across resistor 1, and that would be I1, or it's going to go across resistor 2, that'll be I2, which is to say that the total current going through the whole circuit is equal to the I1 split at the junction plus the I2 split at the junction. But remember, V equals IR. So if V equals IR, then I is equal to V divided by R. Just doing some simple algebraic manipulation there. And so if you can express current by way of Ohm's law as the voltage divided by resistance. And actually, to stay consistent, I'm going to make the R red because you can think of I as the flow of the current, not unlike flow of water, but the resistance is the obstacles that that flow encounters. And so that was the color I used in the previous video, so I'm going to stick to that. So you can think of I as the amount of potential difference there is. And if there's a path provided, there's going to be a flow of charge from higher to lower potential. But then you also have to think about how much resistance gets encountered. And so then going back to this idea of the total current branching off into I1, I2, we can rewrite this equation as the total voltage, and we know that this is 9 volts in this case, divided by whatever the equivalent resistance of the entire circuit is. When a battery, say, or a power source is driving a circuit, it's not conscious of, say, how many resistors are hooked up in series or parallel. It just feels a total resistance. And so that's what we mean with the equivalent resistance. And so continuing, so I just rewrote I total as V total divided by the equivalent resistance of the circuit. And again, that was by way of Ohm's law. And so then the branch, and again, the branch is right here. I'm making the dot a little bit bigger now, where you could either have I1 or I2. And so I1 is going to be V, and remember, the voltage is the same across both the resistors. So I can write V total again. And the resistance across the first resistor is R1. And similarly, I can say the total voltage and the resistance of R2. So I just took that I total equals I1 plus I2. I rewrote Ohm's law, and now I rewrote that equation in terms of V's divided by R's. In each case, the voltage is the total voltage, is the same voltage, because by definition, parallel resistors have the same voltage drop across them. So this term, the total voltage is the same in all three terms. And so it cancels out. And so what you then have is 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. And so what I'm going to do is I'm going to simplify this because I have two fractions that I'm adding on the right. And so what I want to do is I want to get a common denominator. So what I'm going to do is I'm going to multiply one side of the 1 over R1 term, I'm going to multiply by R2 over R2, which is just a fancy way of just multiplying it by 1. And the 1 over R2 term, what I'm going to do is I'm going to multiply it by R1 over R1, which is just another fancy way of multiplying by 1. So if I have R2 over R2 multiplied by 1 over R1, and then I have plus R1 over R1, 1 over R2. So what's going to happen here is you're going to get the following. You're going to get R1 plus R2 over R1, R2. So remember, this is 1 over the equivalent resistance. So if that's 1 over the equivalent resistance, then what I can do is I can just flip the numerator and denominator for both terms, which is to say that the equivalent resistance for these two resistors in series is R1, R2 divided by R1 plus R2. And so do you see how the equivalent resistance for two resistors in parallel with each other is not the same as two resistors in series? When it's two resistors in series, it's just that you add them. But the equivalent resistance in parallel is R1 times R2 divided by R1 plus R2. And so once again, now that we can think of an equivalent resistance, we can take a circuit that was more complicated, and now we can think of it as a simple circuit where it just has a single equivalent resistance, REQ. We have the same 9-volt battery driving the circuit, but the REQ now is this term right here. And you can do the same thing if you had, say, 3 resistors in parallel, 4 resistors in parallel, out to an infinite number of resistors in parallel. All of this stuff boils down to Ohm's law. And the basic idea here is that when you have a potential difference and you supply a path, and that path, when it comes to circuitry, is wire, and then that wire will connect various things that can offer a resistance to the flow of charge. The charge is going to start at higher potential and want to find a path to get to lower potential. As it follows that path, though, it might encounter resistance. When it encounters resistance, there is a voltage drop. However, the way in which the resistance is configured is going to determine to what extent the voltage drops. So to review, in series, if you have, say, 2 resistors, you're going to have 2 different voltage drops. When the charge gets to the second resistor, it's not going to be at the same voltage as it was when it was at the first resistor. However, you can think of a series circuit as having an equivalent resistance where you add the resistors. With parallel configurations, you now have multiple resistors, but each of those resistors has the same voltage drop across it. And so I showed you, also it boils down to Ohm's law, how you can think of the equivalent resistance of a series that has resistors in parallel. And so in both cases, you can take what are ostensibly more complicated circuits and simplify them into much simpler circuits where you can just think of a single resistor offering the equivalent resistance, which you calculate knowing whether you originally had a series combination or a parallel combination.